Okay, so welcome to another video by Agent Data and Pure Electric. This is the third video in this series where I'm going to talk about section B of the AM2, which is the inspection, testing and certification of the composite installation. Basically the installation that you've just installed. Now this is the pre-assessment manual downloaded straight from the AM2, so this is openly available to anyone. I suggest you all download it and have a look before you go through it, because it tells you all the information that you need to know before you go into that assessment. So all I'm going to do is just read through this and break it down. So the maximum time allowed for this is 3 hours and 30 minutes. You'll be allowed 20 minutes to read through this section, prepare for the assessment. This section will be observed by the centre assessor, because obviously they should be making sure with a fine tooth comb that you know what you're doing and that you're safe while you do it. Because some of these tests will be live. You'll begin with the provided documentation throughout the section, and that will be your BS7671. So if you don't already have a copy of this, I suggest you get one and have a look through. They will provide these books on the day, however you don't want to be relying on the fact that you're going to know how to use them. Okay, if you don't know how to use this book before you get there, you're going to waste most of your time working out how to use it. So my suggestion to you is, as with anything, practice using it, practice finding information that you need. With the guidance notes 3, for instance, you definitely need to have this book because it's the inspection and testing side of things. If you don't have this book and you haven't read through it first, your chances of passing are very, very slim. Okay, a lot of us get taught bad practices on site. This is how they want you to do it. So again, unless you read through this and understand the book and understand how to find your way through it and follow the sequence of tests, you're going to be reading every single word in here to find out what's relevant. You're going to waste a lot of your time. Okay, so for instance, I've been through this book and I'm just trying to find a page now. I've highlighted key points that I want to talk about in this video. So rather than having to read through the whole thing, wasting time while you guys wait there on the other side of the camera waiting for me to find the bits I talk about, I've already done that. Now obviously you won't get this on the day, but the more times you read through it, you'll think, oh hang on a minute, there's a bit in here that I want to read through, and it will help you out. Okay, so that's my advice to you. I hear a lot of people out there that watch videos like this one, and that's all they do. They watch videos. They don't bother getting the books. They don't read the books. That's a really dumb idea, because the books are what you have throughout your career, okay, and the books change, so you need to know how to use them. Also, the books are what you get on the day, so again, you don't get videos to watch on the day, you need the books, so you need to get used to using that. Also, I find as well that the books obviously is where all the information is. If you understand the book, you understand your job. I'm a practical person. I like to be shown things and how it works. So for instance, when I first passed at college and I went out on my own, I bought a multifunction tester, which was £800 at the time. It was a lot of money, but then I stripped down my rental property until I understood how to use it and how it worked and why the results were what they were. And I just went through this step by step, doing each test over and over and over again until I understood what was going on and why I was doing it. And that way you're kind of tricking your brain into accepting the information that's in this book through other means. So you read a bit, you do it practically. You read a bit, you do it practically. And that's how you, and over and over and over again. The videos, like this video for instance, and other videos out there on testing, whatever, they help to tie all that knowledge together. So if you don't quite understand what you're reading in the book and you don't quite understand what you're doing, ties the two together. It just ties up any loose ends and fills in the blanks. Okay, that's what videos are good for. Otherwise, you need to get used to reading these books. And unfortunately, it is a cross that we have to bear as electricians, that they constantly renew these books. However, theoretically, we should all be getting paid handsomely for doing it. That's a different subject. Okay, the other book that you get, so you get the BS7671, Guidance Notes 3. The other book you get is the On-Site Guide. Okay, now I'm going to talk you through it. I'm going to talk through each section piece by piece, starting with the model forms as well. And as you can see, I've drawn it up on my board, got a new whiteboard. So I've drawn it up on here. I'm going to talk you through it step by step. Okay, to demonstrate occupational competence, you will be required to carry out a visual inspection of the installation. Now, if you look at Guidance Notes 3, half of this book is an EIC, so Electrical Installation Certificate. The other half is periodic inspection. Okay, so all you're concerned about for this is the first half of the book. So what I would suggest that you do is you work out how many days you've got until your AM2 test, and then I would divide that by the number of pages that you need to read, so 80 pages, and then a couple of pages every day, and just chip away at it, chip away. Chapter 1 talks about the general requirements. Chapter 2 talks about initial verification. It tells you why we're doing it. It tells you what information is required, frequency of subsequent inspections, and the initial inspection, so the procedure, comments on individual items to be inspected, the inspection checklist, okay? So that's what they're talking about here. When you carry out a visual inspection, you need to go through that inspection checklist, and that is on page 33. So page 33 onwards, 2.5.3 talks about the inspection checklist. You need to read through that, okay? So as you're looking through, you're checking for all that stuff. Now, obviously, the better you get at your job, you get used to checking for these things as you go anyway. So for most of us, this will just be a quick flick through, yep, check, all done. And it's not until you get to page 41 that the tests start, okay? So I'm going to leave that on page 41, 2.6.4, the sequence of tests, which I'll come back to later. So, you then have to complete those tests in order. They want you to do the continuity of protecting conductors, so including main and supplementary bonding. So if you think about it in this order, okay, the first thing to do really, or testing, is check that we've got a earthing conductor coming in. We've got a presence of an earth, okay, whether that's a rod, TN, CS, TNS. That's what we're checking for, because without that we can't proceed. So every test that you do relies on the test before, which is why if you change something, you've got to start again and go back through. So you're going to test that you've got a main earth coming in. Now to test that, obviously at the moment, at the start off with, you're just going to do a visual inspection, okay? Later on, you're going to then do an earth fault loop impedance. So do a visual inspection, you've got that from the MET up to consumer unit. You're then going to do your supplementary bonding. Now, if you've installed that, you know it's complete. So as long as it's tight on the, going back for the checklist again, as long as it's tight on the clamps and the clamps are tight to the pipe, you can tick that box. If you're doing it, testing somebody else's work, obviously you've got to test that. Then you've got to do your R1, R2 testing of radial circuits, okay? So then you're testing that you've got line all the way out and CPC all the way back, and then you're checking for polarity at the same time by checking you're switched in the line conductor only. Then you're going to test continuity of ring final conductors. So basically checking that we've got complete rings. We've got no enclosed rings or any broken rings. You're then going to test insulation resistance, which I'm going to talk through later, which is on the other side of that board. We're going to talk briefly about polarity, because once you've tested polarity, it's a really quick test to do. Then once you've done your R1, R2 testing all the way through, you should check polarity anyway. I'm going to talk you through the earth fault loop impedance. Okay, so this is when you start to get onto your live testing from D onwards. So polarity, earth fault loop impedance, additional protection by RCDs, prospective fault current, check of phase sequence, and then functional testing at the end. You then need to correctly complete an electrical installation certificate, which is what I've drawn up here on the board. Well, the schedule of test results anyway, but I'm going to talk you through it. So you need to complete an electrical installation certificate, a schedule of inspections, and schedule of test results using the documentation provided. Now, in the BS 7671, there's a model form, blank. In Guidance Notes 3 and in the on-site guide, there's model forms that are filled out. So section 5, forms, you've got an electrical installation certificate, Model forms for certification. So this is page 121. Okay, so while you're doing this, I'd like you to go through it with your books as well, just to show it. Watching a video all the way through, you're not going to remember anything. So details of client, address, it shows you all filled out. Okay, then talks you through the schedule of inspections, ticks all the way through, where to put not applicables, and schedule of test results. Now, don't follow this word for word, because you obviously need to make it relevant to this installation that you're doing. I'll talk you through what it all means as we go. The thing I want to remind you about videos as well is that I always give the analogy of remembering your best movie, favourite movie, and then trying to play that out in your head all the way through. You won't be able to do it. Time will go quicker. There'll be steps that you miss, and you'll get to the end result, but most of the content of the film is missing. And it's exactly the same with watching content online. So just be careful of that. So you'll be expected to follow practices and procedures that consider the presence of voltage sensitive equipment, which I'll talk through up here. Okay. All testing procedures will be undertaken under the direct supervision of the centre assessor. Then there's a key bit at the bottom here that I want you guys to read. So faults and alterations. Okay. It says there, during and within the time allowed for this section, you may correct any part of your installation that you decide is incorrect or not complete. And this is exactly the same in real life. Okay, this is why inspection and testing is so important, because even though we've installed something, we may have missed something. And then when we're at that testing stage, you can rectify it. Okay, so it is real life, but you've still got the time limit. You've got to do it within the time limit. Okay, so if you do see something that isn't quite right, you are allowed to rectify it. Only once you've installed it and tested it do they then strip it down and reassess it. So when you do this, make sure you put everything back together again. When you take all your cables out and you put them back in again, make sure they're tight and that they're tested tight, okay, tug tight, they're in the right connections, everything like that, because you may have installed it correctly, but once you've tested it, you may have put it back in correctly. And just like in the real world, that's not good. Okay, so you need to apply this to a real world situation, that your boss has sent you out to a job. You've got to then install that job, you've got to test that job, and if you mess it up, it's going to cost money. Okay, could endanger lives. Okay, it then goes on to the common errors. So candidates do not prepare the instrument for use and set it on the correct range. Okay, now what that means is selecting the correct functional voltage. Now, if you haven't picked up a tester before, I don't recommend going straight into the AM2 until you've done it. You know, you need to get a tester, you need to practice using it. I was speaking to someone a while ago on LinkedIn, I think it was, and they were saying that their company used to give the apprentices 2 months of pure testing before the AM2 to get used to the testers themselves, get used to the process. I mean, that's an amazing, thing to happen. I mean, why that doesn't happen more, I don't know. Remembering to null or zero the leads. Okay, so when you get given a tester, if it's not your tester, you haven't used it for a while, you need to get yourself familiar with it. Okay, you need to read the instructions, make sure you understand how to use it. It may not be the tester that you're used to. Okay, so you need to take some time to get used to how that tester works. I would like to think that they've left a manual there that shows you how it works, because otherwise that would disadvantage a lot of people. You know, if they were providing mega testers, for instance, and you're used to using a fluke tester, it's going to be a bit confusing when you get there. So hopefully they've left instruction manuals around for you to use. Whenever you get a tester, even if it is your own tester, you need to prove that it's working. All right, you need to check that obviously you've got calibration, it's in date. You need to check that the batteries are okay. Okay, so whenever I had my yearly assessment, competent person scheme assessment, I'd always have a pack of spare batteries just in case, because sod's law, on the day they would be dead. So I always have spare batteries. You want to check that your leads are okay, that there's no damage, that when you switch it on, the display's working correctly. And then you want to, if you're doing each test, say for instance continuity, you want to put the probes together. The gate should close, and then you should have continuity, and then when you pull them apart, the gate should open, and then you won't have any continuity. Okay, so you get a reading, no reading. get a reading, no reading, then you've proved it. Don't forget to null your leads. So you put the leads together, okay, and then you null the leads so that you've taken the resistance of the lead out so we can get the most accurate readings possible. Resistance, okay, you need to do the same thing. You need to put them together. You should get no 0.00. You're getting continuity, okay, so there's minimal insulation resistance possible, okay. Take them apart and you should get greater than 299 or 599, whatever your meter is set to at the time. You're getting maximum resistance. There is no continuity, okay. So together, continuity, apart, no continuity. So small insulation resistance, large insulation resistance values, all right. Don't forget to test it. Your inspector is going to make sure that you're testing it. Now, 2 reasons that you're doing it is that A, obviously you're making sure that you've got the meter connected up right, the leads are nulled and they're working, but also that you've put the leads in the correct slots on the side of the unit or the front of the unit, back of the unit, whatever. Because if you're not getting any reading, then you're not going to get any results. Okay, so if you think that you've just picked up this tester, bang the leads in the side and start cracking on, and the person who's assessing you sees that you haven't put the leads in correctly, well, they're just going to walk off because there's no way you're passing this test because you haven't put the leads in the right place, okay? So just be aware of that. You need to make sure the meter's working. So candidates do not carry out the test in accordance with BN7671. So it says here, you have the on-site guide with you, so if unsure, check how the test should be carried out. Personally, I would suggest that you go through the guidance notes 3 and use that book step by step. Do not take shortcuts you have been shown on site. These may not be correct. Follow the way you have been shown in college. What I would say is even that might be a bit fuzzy, but if you've got guidance notes 3 in front of you, literally page, do that test, turn the page, do that test, and literally page by page. If you remember something and need to go back and repeat a test, that is fine if you repeat any other tests that rely on the test being carried out. Okay, so for instance, when I get through this, if you're doing continuity of ring circuit conductors, okay, and then you move on to R1, R2 testing and realise you've done something wrong, then you need to go back and do R1, R2 testing to then be able to get this one right, if that makes sense. So each test relies on the test afterwards. For instance, you can't move on to insulation resistance if you suddenly realise your R1, R2 test was wrong. You need to make sure that it's all correct all the way through. Remember on lighting circuits to operate switches when required and parts of circuit after isolators or contactors. So if you've got a switch fuse spur that's doing a socket, or it's doing a smoke alarm or something like that, other than the boiler circuit, because you can't test that past the switch fuse spur, you need to make sure those switches are on and you're testing all the way up to the appliance. Okay, when you're doing your testing through your intermediate switches, you need to start at one switch, press it, next switch, press it, last switch, press it, then go back again. Middle switch, press it, so the intermediate, then the first switch, press it. Then you've done all the strappers in that circuit, okay? If you don't do the strappers, then you haven't tested the circuit fully. It may not be connected up right, which means that when you come to get the R1, R2 reading off the end, you haven't taken it through all the way through. You also haven't proved that the switches are connected up correctly. Candidates do not record the test results. So this is normally when someone carries out testing and records results on a scrap piece of paper and then at the end cannot find the reading they require. So what I would suggest to you is on the back of your electrical certificate, I'm going to show you what to write out and what to draw to prove what you're getting is what you should be getting, okay? But anything that you do, keep it on the back of the certificate. Some people fill in the schedule of test results wrong. So as you're filling out the schedule of test results, and do it as you complete each test rather than trying to fill it all in at the end, because this will also highlight anything that you may have forgotten. Okay, if you look at the test certificate, it is in a logical order. It doesn't jump around too much. It's kind of in a step-by-step process, which I'll talk you through. Candidates do not verify test results obtained against the requirements of BS 7671. So the results need to be compared with the maximum values to check if they were within range allowed. You may know the maximum values, but to prove this, they need to be documented on the scheduled test results. Okay, so again, that's something like having your maximum ZS, which is over here, which you guys can't really see at the moment, but your maximum ZS from page 62 in the regs book and table 41.3, it's your maximum ZS. Then comparing that to your measured ZS, which would be your ZE plus your R1 plus R2, and then comparing that to the 80% value that will be in the on-site guide. Okay, so whatever the maximum is in the regs book, so let's say for a 32 amp MCB or RCBO, it's 1.37 ohms. The 80% value is 1.1 ohms. Okay, so this value measured needs to be lower than 1.1 ohms, not the 1.37. Okay, which I'll talk through as we go on. You want to check things like that. Okay. You also, as well, while I'm on the subject, you need to make sure that any insulation resistance values that you get then correspond, because obviously you're testing resistors in parallel, which I'll come on to in a bit on the other side of that board, but you need to make sure that you test the reciprocals of all those over the whole installation, and that's greater than 1 megohm for the whole installation. It's not 1 megohm per circuit. Okay, so you need to know that as well. You also need to know that in guidance notes 3, on page 51, it talks about insulation resistance for a new build or for a new installation. So this paragraph here, right above the picture, okay, so that says there, although an insulation resistance as low as 1 megohm would comply with the requirements of the regulations, a new installation should not yield a test result this low, and in new installations a value below 20 megohm should be investigated. Okay, and I'm pretty sure they're going to want to know that you know that, or you've seen that caveat. And the reason that caveat's in there now, because this only came out in the 18th edition version, I'm pretty sure that caveat's only turned up now because people were literally banging in new installations and then passing a 1 megohm insulation resistance test, when that shouldn't be happening. You know, it's virgin cable, should be brand new, greater than 299 all the way kind of thing. Okay. So, candidates do not complete BS 7671 inspection 7 testing documentation correctly and accurately. The test documentation is a legal document and needs to be completed correctly. There are templates in the on-site guide and guidance notes 3 showing you how to complete these documents if you are unsure. As you go through as well, if you look on the model form, it does have all the reg numbers there if you needed to check what it means. You may test correctly, but if the documentation is not correct, the testing would not be proven as correct. Okay, which I understand, because giving the apprentice a tester and telling them to run around, get all the readings, record the highest, well, that's great. The apprentice thinks they're doing testing, but actually they don't know what any of those results mean. They don't know if it's a good result, a bad result, or how it ties in to anything or how it works. That's not testing. That's just running around with a machine, recording the highest figure. So you need to understand why we do what we do. Candidates do not verify that the installed circuits and equipment function as intended. So checking that the installation works as required before handing it over is important. If the installation did not function, this would require revisits by someone to correct, and you and your company reputation could be damaged. So again, this is a real life situation, okay? Now, if you don't install something correctly, and your boss is charged £200 to be there for the day, and then you have to come back for a second day or a third day because you haven't done the right things and you haven't tested to make sure it works, well, your boss has just lost money. You've lost money if you go out by yourself, you know, and that's what this is all about. You don't get unhappy customers that won't use your company again. I remember when I was at college, training to be a mechanic many years ago after I left school, but the lecturer there said, if you do a good job, 2 in 10 people hear about it. If you do a bad job, 8 in 10 people hear about it. And that's true. Bad news sells, and it moves fast as well. So, you know, company reputations can be damaged instantly. You know, how many times have you left a review for something you were happy with compared to how many reviews you've left when you're unhappy with something? So, you know, proof is in the pudding. Okay. Candidates do not reinstate connections correctly. So this confirms what I was saying before. While testing, connections have been disconnected to carry out testing. It is important that connections are secure after testing. They are tested after the installation has been tested, so you may cause an issue to a connection that was okay before testing if you do not re-terminate it securely. And what that means is basically when they start stripping your board down, if it doesn't work, you won't pass. So you may have installed it correctly, but when you came and did the testing, you rushed through it, or you connected something up wrong because you were a bit flustered or not quite paying attention, you'll fail, okay, even though you did the install correctly. Right, okay, so that's that. Now, what I would suggest then is we're going to start talking through the model form. Okay, so I'm literally just going to turn to page 462. So page 462. Now, if you're going to watch this video, you need to have the book in front of you, because otherwise I'm just going to be talking for ages, and this isn't going to make any sense. Okay, so get the book out, page 462. So details of the client. A lot of this will hopefully be filled out for you, okay? Details of the client, if it's not in there, just put AM2 Centre wherever it is you are. Your installation address, so that would be the address of the AM2 Centre. Description and extent of the installation, so basically you would put in there your AM2 bay and whatever number AM2 bay that is. Extent of the installation covered by this certificate. It only gives you a small box, but in there it also says use continuation sheet if necessary. So that kind of gives you an idea of what you should be filling in there. It's going to be quite a lot of information. Now, for this AM2 or the AM2S, all you're really doing is installing that and then describing what's in it. In the real world, you need to get as much information in there as possible, or as you see fit to cover your backside. Because if you put on there downstairs lighting, okay, and then there's a fire, but it's not on the section that you installed, if it ever goes to court, the judge is going to look at it and say, well, you installed the downstairs lighting. You say, well, I didn't install that part of the lighting. And the judge will say, well, that's what it says here, okay, and you're out of pocket or you're in trouble. So for instance, if I was doing it in our house, I would say, for this room, I would say lighting, change lighting or installed lighting and switching in first floor office, comprising of one switch, one light point, pendant, okay? Just a level of detail like that, just to cover my backside, so that if the customer ever phones me up and says it's gone wrong, I'll say, well, where's the certificate? And it could be years down the line, by which time you've forgotten what you installed. I'll look at the certificate, oh, well, yeah, that's what I installed, that jogs my memory. So where's the problem? Well, that's next door, that's in a different room, I haven't touched that, that's nothing to do with me. I'll check the connection from this point onto that room, but if it's anything past that, that's extra cost, okay, and I'm not covering that. So just be careful, you want to cover yourself. You then get a chance on the side to tick these boxes. So we've got new installation, or addition to an existing, or alteration to an existing. Well, this is going to be a new installation, okay. It then says for the design. Now, you haven't designed this job's been designed for you. You should get a candidate specification, which tells you everything that you need to install and how to install it. So for the design, this should be filled out, okay? You need to move down to for construction. Now, in that top bit, you need to put in the date that it was amended. So the 18th edition was amended in 2020. So you need to put amended to 2020. Details of departures from BS7671. Well, it's my understanding that there's some SY cable that's installed. Okay, so if they've installed SY cable, that is a departure from BS7671 because it doesn't have a BS number. The extent of liability you need to sign and date it, block capitals, and also for the inspection and testing. Now, there's no details of departures on the testing, okay, because we can test that SY cable, so you don't need to fill that in. But again, you just need to put in there 2020 if that was the amendment date, of the 18th edition. If it, we get Amendment 2, it would be that date, and so on. And then the next inspection, you need to choose an interval for it. Okay, to enable you to choose that, you need to go to page 87 of Guidance Notes 3. Okay, and it will tell you. So if you're looking at the installation and it's purely domestic, it would be 10 years or change of occupancy. If you were looking at commercial, it would be 5 years or change of occupancy. And if you were looking at industrial, it would be 3 years or change of occupancy. And there's a few other little different ones in there. So you need to look at the installation and think, what have I got here? Is it domestic? Probably not. Is it industrial? I think there's some office sockets, sockets or dado trunking, so it's probably more likely to be commercial, but you need to look at that. But page 87 will help you out, okay? Right, that's the first page done. Easy peasy. Then you've got particulars of signatories to the electrical installation. Again, you're not the designer, so you can't fill that in, but you are the constructor, you are the inspector, so you need to put your company, your address, postcode, telephone number. You then have to choose the earthing arrangement. So most installations these days are TNCS. Even if it is TNS at the head, it's probably TNCS in the road. However, you need to comment on whatever's on the head. In this scenario, I'm pretty sure they tell you what you've got, and I would be very surprised if they didn't give you TNCS. But double check. I'm told that there might be a sticker on a whisker box or something that you need to look at. Number and type of live conductors. Okay, so it's 3-phase and there's a neutral, so it's going to be 3-phase 4-wire. Big tick in the box. Confirmation of supply polarity, well, you can't tick that yet until later on, but you need to remember to come back to that. You then got the nature of supply parameters. So nominal voltage U, so that will be 400 volts, and then /UO, so that will be your phase voltage, which would be 230 volts. Nominal frequency, prospective fault current, okay, so that's your Ka value. Now, if you're testing at the supply, which you're not, that's what you would record. Because you're not testing at the supply, you need to check what they want you to put in there. They may have already filled it out, okay, because this is the supply parameters that you're supposed to be filling in. So they may give you that, or it may be in the specification. I don't know. You're going to have to, when you get there, you're going to have a look and see or ask, okay? Now, these assessors are there to help provide guidance. They can't tell you the answers, all right? And, they just point you in the right direction. It then talks about external loop impedance, so your ZE. Again, you're not at the installation coming in, okay? So not the supply installation, supply should I say. So you can't measure the ZE. You're going to be measuring the ZDB, okay, because you're going to be at distribution board. So you can't fill out that ZE unless they give you the information for that. In the real world, you could do by inquiry, which we know for a TNCS, for instance, is 0.35 ohms. That's your maximum. Prospective fault current, well, you could, again, phone the DNO and ask them, or you could put the prospective fault current of the protective device. On page 71 of Guidance Notes 3, table 2.8, okay, so that tells you your rated short circuit capacities of protective devices. So you could, for instance, if you had a BS 1361, which they don't have so much anymore, but that will be now a BS 88-3. If it was a type 2, theoretically you could have 33 Ka. Right, so you need to work out what your Ka rating is depending on the installation that you've got. There isn't a one size fits all. You need to look at the supply head. You maybe need to talk to the DNO, etc. You've then got your supply protective device. Okay, so this is going to be the fuse that's in the head. Again, I don't think you have that, so they'll probably tell you what it is. So that might be a BS 1361, or it could be a BS 88. It will say on there. Type could be 1 or 2. Again, it will tell you, and rated current. So because this is 3-phase, you'll probably find out that it's 125 amps. I'm guessing, but have a look, it should tell you. You then got particulars of installation referred to on the certificate. So means of earthing, distributor's facility, because we don't have an earth electrode. Your maximum demand. Now, because this job's been designed for you, I would like to think that would be in the specification, or it's already filled out. In the real world, you know, you would either work it out through diversity. Again, you're going to have to ask what they want you to put in there. Details of installation earth electrode. Well, we haven't got one, so you can't fill that out. Main protective conductors. Okay, so this, you know, you can start to see that this is nicely laid out. It tells you exactly what they're looking for if you follow it in order. So earthing conductor. So that's from your MET up to your consumer unit. Probably find that be 16 millimeters squared minimum. It may be 25, who knows. Material, and then CSA size. So most likely it'd be copper. Then you've got your main protective bonding conductors. So that's your extraneous conductive part. So extraneous means it's going to earth and it's external to your house. Again, material there, copper, CSA, most likely 10 millimeters squared. And then you tick the box that says connection verified. So if you can see it, you can tick it. If you can't see it, you've got to test it, okay? And prove it. And then you tick whether it's water or gas, oil, structural steel, lighting protection, other, and then it says specify. Now we're moving on to the main switch, okay? So the location for this main switch is going to be your AM2 bay. Most likely it's going to be a BS. I don't know if you guys can see that up there. Most likely it's going to be a 60947-3 isolator. And it'll probably be, because it's 3-phase, it'll be 125 amps. Again, you're going to have to check a number of poles. It's going to be 3-phase. If the neutral switched, it's 4-pole. If the neutral isn't switched, it'll be 3-pole. So you have to look at the size of the switch, how many poles of that switch is there. Okay, if you think back to a domestic, you've only got 2-pole, 1 live, 1 neutral. Here you're going to have 3 lives, and then it will be 3 lives and neutral, so 4. The current rating, that should be written on the front of the switch, so I'm guessing 125 amps, but please make sure. The fuse device rating or setting, well, that's not applicable because it's not a fuse. And the voltage rating will be 400 volts. Should be written on it. If RCD main switch, which you don't have, so that will be not applicable. Now, one thing I want to make sure with this, guys, is as you go through, if there's any boxes that don't need to be filled, you put not applicable in the box. You never leave a box blank. Comments on existing installation. Well, this is new, so you can put in there not applicable. Schedules, so there's going to be 1 set of schedules and 1 set of test results. So you can just put 1 and 1. Then we're going to move on to the schedule of inspections. And that's on page 471 of BS 7671. Right. Okay, guys, so I'm going to talk through the schedule of inspections for a new installation, okay? But rather than go through BS 7671, I'm actually going to use Book 1, Electrical Installations book by Peter Tanner, okay? The IET City and Guilds endorsed. On page 365, okay, on 364 even, it's got your safe isolation procedure, which you should have done earlier. And then on 365, it starts to talk through the schedule of inspections, okay. Now, when I saw this, I thought this is an amazing resource for apprentices to have. You know, it's got each thing that you should be checking from 1.1 all the way down, and it tells you what you should be looking for and how, okay. So if you haven't got this book already, I highly suggest that you get it. I mean, if you're going into the AM2, you probably want to get book 2, because it has more in-depth testing. Book 1 is really just R1, R2 testing and insulation resistance. So book 2 would be better for you. And it talks through each individual test, tells you why you're doing each test and the expected results that you should get through. So I highly recommend the book, to be honest with you. So I'm just going to flick through here. So items number 1.1 all the way down to 1.6. Well, that's the supply that's coming in. So unless you can see the service head, earthing arrangement, meter tails, I don't know what you can put in there. So you have to ask your assessor what they want you to put. It may even be filled out. I'm assuming you can see some meter tails. There must be something coming up. So as long as they're in good condition, you can tick the box. Metering equipment, I'll be very surprised if there's an electrical meter there. There may be an isolator present. So if there's an isolator, you need to make sure that the IP rating of that is fine and that it's all working. So it says here, all these items should be checked for their levels of basic protection against electric shock and how well they are fixed securely, that they are located for easy access for maintenance or proximity to other services such as gas. Inspectors should also look for signs of damage, tampering, and that all tails remain insulated to all terminations. Okay. You then go down to number 2, which is parallel switch supplies. That is only generating sets or PV, something that's basically bringing another voltage into the building. So for that, you can put not applicable if it's not there. So again, don't leave any boxes blank. It's either a tick or not applicable. We're not doing an EICR, okay, so it's not a condition report, so there should be no C1, C2s or C3s. Because this is a brand new installation, it's either a pass or not applicable. If you come across something that you've forgotten, then you need to sort it out, okay? Because it needs to be perfect and pass. We've then got automatic disconnection of the supply. So it talks about the earthing conductor. This needs to be suitably sized, continuous. So if not visible throughout its length, it may require testing to confirm this. Connections are tight, suitably supported. Main protective bonding conductors, again, suitably sized, and that you can see all the cable throughout its run, or you've got to verify it, and connected to, at the points of the extraneous parts within 600 mil of entry on the consumer side of any valve. Connection secure and the correct type of clamp used for external influences. So if you have used bonding clamps, you need to make sure that they're tight, they don't move on the pipe. So really grab hold of that and make sure it doesn't move. If you've used the what I call the metal ones, I get some long nose pliers on the side of that, on that tag that you push through, and I wind that up really tight with a set of long nose pliers, like a tin of sardines, and get that really tight, and then I do it up tight after that. If you're using the easy clamp system, then you need to make sure that the label is pointing upwards so that it can be read. And if you're using the metal one, then obviously you've got to make sure that the earth bonding label is on the front of it, okay? Because without it, it doesn't pass. Now again, I don't know what contributes to a major or a minor, okay? Provision of safety electrical earthing labels, that's what I was just speaking about. RCDs provided for fault protection. Well, unless you've got an RCD main switch, I think you're just doing it for additional protection. Okay, so that will be your 30 milliamp RCDs. Insulation of live parts. So all conductors should be insulated with material suitable for the intended voltage. The insulation must cover conductors right up to the terminal or connection with no bare conductor showing. So again, when you are looking at the MCB, the conductor should be straight up to it, no insulation, no copper showing. When you bend it back, copper showing. So all at 90 degrees. All barriers and enclosures provided, adequate protection, so any top surface, horizontal surface should be IP4X, so 1mm tall. Everywhere else, IP2X or XXB apply to all surfaces with exception of any accessible top surface, which is IPX4. Live parts must only be accessible by the use of a tool. So if you're looking at the front of the consumer unit, you need blanks in there. And there are some exceptions such as ceiling rows, but these items must be located in a generally inaccessible location such as the ceiling, where a person steps to access. So what they're talking about there is the bayonet fitting. Obviously you can get your finger in that all the time. A lamp's in there, you can't get to it, and it's also out of reach. RCDs. So where additional protection is provided, so if you've got sockets, you'd have additional protection. RCDs in accordance with 415.1 are used, so it must be confirmed that the RCDs are rated with a residual current setting no more than 30 milliamp. So methods of protection, it talks about selve and pelve. You don't have any selve, you don't have any pelve. Double or reinforced insulation, so you do have class 2 equipment there, so that would be the motorised valves on the boiler system, and I think the light you may have maybe class 2 as well. And then electrical separation for one item of equipment, e.g. a shaver socket. We don't have one of those, I'm pretty sure, so that would be not applicable as well. Then we like the consumer unit. So adequacy of access and working space for items including switchgear. The inspector must be satisfied that all switchgear and control equipment are fully accessible for use and maintainability. It's a huge space for your AM2, so you should be fine. Presence of a linked main switch. Can the consumer unit or distribution board be isolated by one switch action? It must be clearly labelled. So again, it's one linked switch all the way across, big tick in the box. Isolators, so suitable means of isolation provided for an installation and circuits. Devices should be capable of being locked off in the off or open position. Okay, so you've got isolators, the MCBs, so the big tick in the box there. So isolators for every group of circuit. Again, we've segregated the circuits, so we can tick that box. Suitability of enclosure for IP and fire ratings. So the housing must provide basic protection and must be suitable for fire ratings for the intended location. So any consumer unit or DB installed within a dwelling must have a suitable fire rating such as a metal enclosure. 7.6 Protection against mechanical damage where cables enter equipment. Cables entering the enclosure must be provided with suitable mechanical protection such as glands, grommets or edging strip. 7.7 Confirmation that all conductor connections. Connections must be tight and checked to ensure that good connection to the conductor exists and terminations aren't clamped onto the insulation. So again, you should be looking through this schedule of inspections because this is going to help you pass. Don't just read down and go tick, 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 tick. You need to read through it and make sure you understand what's going on. Again, tug test for that. So 7.7 tug test. And if they do have them, use your torque screwdrivers because every consumer unit now, the manufacturers stipulate that you should use the torque settings. 7.8 Avoidance of heating effects. So where conductors pass through metal enclosures, lines should be run with their corresponding neutrals to reduce heating effects caused by induced eddy currents. 7.9 Selection and correct ratings of circuit protective devices. So are the right type of fuses or circuit breakers being used? Again, this has all been in the specification for you, so that should just be a big tick in the box. Provision of circuit charts and information. I'm told that all of that is there for you. Warning notices for isolation. So there should be labels on the board. RCD test notice, if there should be one there. Warning of non-standard colours present. This is a new installation, so there shouldn't be any non-standard colours. And presence of labels to indicate the purpose of switchgear or protective devices. So your board should be labelled. 8.1 Adequacy. So we're now talking about circuits, okay? And this is all, it tells you at the headings, every single one you go through, it explains what you're doing. So now we're on the circuits. 8.1 Adequacy of conductors for current carrying capacity. If you followed the spec, then you've done that correctly. 8.2 Cable installation methods. Again, if you followed the spec, you've done that correctly. 8.3 Segregation, separation of circuits. A lot of people go wrong here. So when you do that data cable, you can't run it in with the power cable and you've got to have it in a separate compartment, and when it crosses over, it needs to be segregated with a bridge. So as long as you've put that in, you can tick the box. 8.4 Cables correctly erected and supported. The inspector must be satisfied that all electrical equipment, cables and containment systems are suitably and securely installed. As an example, does a conduit have adequate saddles which are correctly spaced? Now I'm told all the saddles are done for you and you're not allowed to move them, so that should be a big tick in the box. 8.5, provision of fire barriers and ceiling arrangements. Okay, so the inspector must be satisfied that all electrical equipment provides suitable protection to stop the spread of fire or thermal effects in accordance with Chapter 42. It must be verified that elements of the building structure affected by the installation, such as trunking, passing through floors, are adequately sealed. 8.6, non-sheathed cables enclosed throughout. Does the containment system have the correct IP ratings where non-sheathed cables are used? 8.7, concealed cables adequately protected against damage. So if cables are not in the zones of protection as described in Regulation 522.6202, they must be protected by an earth metallic covering. Again, I don't think you have any of that, so that would be not applicable. 8.8, conductors correctly identified. So all conductors must be clearly identified by colour or marking. This includes sleeving of conductors. The inspector must be satisfied that all conductors are in accordance with Section 514. 8.9, presence, adequacy and correct termination of protective conductors. This is to verify that all protective conductors other than those verified in 3.1 are selected and correctly terminated to all equipment as required. So you should have done that when you did your R1 to R2 testing. 8.10, conductors and cables and conductors correctly connected and enclosed. All cable connections must be durable and of the correct type for the application. So 8.10, cables and conductors correctly connected and enclosed. So all cable connections must be durable and of the correct type of the application. So things like your Wagos need to be the right size rating and good condition for what they're used for. 8.11, no basic insulation of conductors visible outside enclosures. So sheathed cables must have the sheathing present up to the enclosure with no core insulation, so no basic insulation, that's your brown or your blue or whatever, showing outside of that enclosure. 8.12, single pole devices for switching and protection in line conductors only. The inspector must be satisfied that all single pole devices control the line conductor of the circuit and not the neutral. This includes circuit breakers, fuses, switches, etc. 8.13, accessories not damaged, securely fixed, correctly connected and suitable for external influences. The inspector must be satisfied that all electrical equipment is suitably selected and erected for all external influences it may be subjected to. Okay. We then move on to 8.14, so provision of additional protection for RCD. So if you've got some sockets or lighting in a bathroom, then you will have additional protection. So socket outlets at 32 amp or less unless exempt need to have RCD protection, so big tick in the box. Mobile equipment not exceeding 32 amp for use outdoors. So if you had an outside socket, that would need to be RCD protected. Cables concealed in walls up to a depth of less than 50 mil. Well, I'm pretty sure you're not burying anything in the wall, so that would be not applicable. Concealed cables in walls or partitions having metallic parts. Okay, so I don't think you're installing in any walls metal stud walls, so that would be not applicable. Switching for mechanical maintenance. So any item of equipment that requires mechanical maintenance, so non-electrical work such as cleaning filters, tensioning bolts, etc., must have an appropriate switch located where it can be supervised during those maintenance tasks. If they cannot be supervised, then the switch must be capable of being secured in the off position. Emergency switching. This sometimes catches people out, this one. So certain items of equipment may require a means of stopping the equipment in the event of an emergency, such as a rotating machine. Stop buttons, okay, are an example, and an inspection would determine that they are the correct type. So latch able or key latched as an example, and located in a readily accessible position. I think that's supposed to read latchable. Functional switching or control. So all current using equipment must have a switching device which controls the equipment or several items of equipment. An example would be a light switch. Firefighter's switch. So certain equipment operated at high voltages require control using a firefighter switch, but I don't think you have any of those, so you should be okay. Now we're on to 9. So 9.1, equipment not damaged, securely fixed and suitable for external influences. So again, equipment must be suitable for all external influences it's subjected to. This would include equipment being mechanically sound and having suitable IP protection, such as IP4X for equipment installed outdoors where splashes of water from all directions are likely. So like an outside socket, for instance. Presence of overload and undervoltage protection. So equipment such as motors must have an overload device set correctly for that equipment. So if the machine jams, the overload device functions. Now, if you were installing a DOL, for instance, you would need to make sure that the rating of the DOL was capable of switching off if that happened. Undervoltage protection, so again, that's a DOL to motors, may be provided by a contactor such as a DOL starter. So this stops the equipment from suddenly restarting should a power loss occur. So imagine you've got a double socket and you've got a plug switched into that. And if that switch was on and the power got cut, the machine would fail, stop working. But as soon as the power was re-energized, the circuit would then become live. The machine would then start up again. So what a DOL does is, because it works under magnetism, when the supply gets cut, the switch then switches off and has to be physically engaged again. So when the power comes on, the machine doesn't start up by itself. So 9.3, installed to minimise the build-up of heat, restrict the spread of fire. So equipment must be suitable for the material it is mounted on, okay? And suitable when a risk of fire exists due to the stored or processed material. It must be verified that the equipment is suitable by mark or specification. Example may be a luminaire mounted on wood should carry a mark such as a D within a triangle showing it has a limited surface temperature. Okay, so just bear that in mind. 9.4, adequacy of working space and accessibility to equipment. Well, you've got plenty of space there, so that'd be a big tick in the box. Then moves on to locations containing a bath or a shower, but I don't think you have any of those. And then any other special installations or enclosures, that would be as given in part 7. I don't think we have any of those. So that is your checklist basically. You should be working your way down that. That's the schedule of inspection. Next we're going to move on to the installation certificate, which is behind me, and that will be on page 483. So again, make sure you turn to that page while we're going through this. Okay, let's now talk through the schedule of test results. So what I've done is effectively the model form, which is on page 483. 483, which we're looking at here. Okay, I've literally just copied that up onto this board to save me having to keep poking this up at the thing, up at the camera. So effectively what you're going to have is the DB reference number. So this, you either look on the board that's there or you look in the specification. If you're not sure, ask. Chances are it may already be filled out. The location is going to be your AM2 bay. The ZS at the DB, so let's call that a ZDB because you're not connected to the supply. Okay, so let's call it a ZDB. You will measure this. Same with the perspective fault current at the DB, you'll measure that as well. Okay, that will be a live test. So your assessor will hopefully should be standing beside you while you're doing it, making sure you're safe at all times while you're doing that. But again, because it's a live test, you'll get all the dead testing first done, and then you'll move on to the live testing. Correct supply polarity confirmed and the phase sequence confirmed. Again, you will have to test that with the live testing. The phase sequence confirmed, that will be when you've done your R1, R2 testing all the way through the circuit. So once you've done all that, then you can tick those boxes. Tested by who? So who's taking responsibility for this installation? That will be you. So your name, capitals, sign and date. Obviously anything that you put a signature and date on becomes a legal document. So just be aware when you're filling these out in the real world, you're taking responsibility for that installation. And if you're the QS, then you are legally responsible for taking control of that. I think there was a case, the Emma Shaw case, if you guys look that up, and it was a QS that was prosecuted, not the company. Okay, so just be aware when you're signing these things off, you're taking responsibility. I'm sure there was more to it than that, but worth looking. It's called the Emma Shaw case. Have a look. Okay, so circuit details. One of the things I want to sort of talk about here is in guidance notes 3 on page 127. So on page 127 of guidance notes 3, there is a generic test results for a 3-phase installation. Okay, and one of the things that I just want to point you out to here is just this sequence of circuit details, circuit numbers down the side here, and I think they've got that wrong. I don't know if you can see that very well. I'll read it out to you, but effectively, if you look at the circuit number, it's got 1 to 12. And then it's got L1 ring ground kitchen, L1 radial kitchen, L1 radial fire alarm, L1 lighting ground floor, L2 ring ground floor, L2. It just doesn't make any sense whatsoever. That should be 1 L1, 1 L2, 1 L3, 2 L1, 2 L2, 2 L3, all the way down. So just be a bit careful if you're using this model form in your AM2 to not let that catch you out. Okay, so hopefully you guys can see over here that I've put, so I put 1 line 1, 1 line 2, 1 line 3, so those together would make 3 phases. Then I've got 2 L1, 2 L2, 2 L3, and they would be blocked together, and then it would move on like that: 3 L1, 3 L2, 3L3, etc., etc., all the way around the board. So just be aware of that if you're following guidance notes 3. I'm just going to leave guidance notes 3 open on page 41 because that's where the schedule of tests is going to begin. When you're looking at this part of the certificate, so the circuit details, up to the ring final circuit continuity, so up to that line there, that's just data that you're collecting off of the consumer unit. So obviously you've written in the circuit numbers, you've written in the circuit description. Again, all of that will be given to you. It should be in the specification. The type of MCBs that you're using, they should have been in the specification as well. So again, all of this is just copying that data over, as long as you've obviously installed the right MCB or the right RCBO. So the type of the MCB or RCBO, that will be B-type, C-type, D-type. The rating of the protective device, that will be on the front of it, so whether that's a 6 amp, 16 amp, 32 amp. And the braking capacity. Now a lot of people struggle with this. The braking capacity, I'll quickly turn this over, hopefully you guys can see this up here. I might have to bring that over quickly, bear with me. Take that out. That should be on the front of the MCB. So for instance, I've got 60898, which is an MCB, and I've put in the square box, there will be a figure. It will say 6,000 or it could say 10,000. That's the braking capacity. And then obviously we've got the B, which is the type, 6, which is the rating. RCBOs are 61009s. Again, I've put 6,000, it could be 10,000. And this one I made it a C32. Okay, so that's a different type and a different rating. Okay, so just be aware of that when you're filling that in. Don't just start doing it from memory. Just make sure you're getting it right. Okay. So as I was saying, all of this to that point there is just data. RCD, well, you only need to put in the milliamps if there's an RCD on that circuit, so chances are it will probably only be on the socket circuit. So for the socket circuit, you just need to put in 30 milliamp for additional protection. Your maximum ZS, well, you're going to get that from table 41.3, which is on page 62. Okay. So that will be this chart here. And all you'll do is you'll just scroll along. So you'll select the level, whether it's a B type, a C type or a D type. you'll scroll along with the current rating at the top. So if we were looking for a B6, for instance, that would be 7.28. If we were looking for a C32, so C32, that would be 0.68. So just be careful that you get the right ZS in there. That's the maximum ZS. Okay. So that's the max ZS goes in there. And then the conductor detail. So the reference method. Well, that reference method, the easiest place to probably look is in your on-site guide on page 155. We've got current carrying capacities in Appendix F. And then we've got A, so enclosed in a firmly insulated wall. We've got B, which is enclosed in conduit on a wall. And we've got C, which is clipped direct. And then we've got reference method F, which is on perforated tray or in free air. Now the difference in this, if you can see this on here, if you take a piece of 2.5 for instance, which is here, if we're in a firmly insulated wall, we've got 20 amps. If we're on a wall, so that's in conduit, sorry, in a wall. If you're on a wall in conduit, so you're outside of the wall, you gain 4 amps because the heat from the cable can dissipate. Whereas in here, you're in a thermal insulated wall, you can only get 20 amps. Then as well, if you go along to clip direct, we're up to 27 amps now. So we've gained 7 amps from being inside a wall or clipped direct. And then obviously tray, it would be just 27. So that's what you guys need to be careful of when you're installing, is that the reference method, the way you install it, can directly affect how that cable can dissipate its heat. If you were to look in the regs book, for instance, okay, and then look at table 4A2, which is on page 386, okay, which is this here. Again, this is the reference methods, but it shows you pictures to try and help you work out what type of installation method that you've got. And one of the things that I want you guys to take away from this is if you turn to page 390, okay, here we've got reference method 100, so thermal insulation less than 100 mil. We've got 101, which is thermal insulation greater than 100 mil. Then here we've got insulation value with cable touching the inner wall surface or touching the plasterboard. And then 103, basically not touching plasterboard, so in the stud work and down the center of the stud, you know, so in the insulation. So if it's on wood, not plasterboard, without one side touching, because look here, that's got one side touching, so the heat can dissipate through the plasterboard easier. Here, because it's right in the middle, it's different. So if you turn to page 409, that will explain the difference, okay? So that's here, 409. Now, exactly the same thing as the way it's set out in the on-site guide. But if you look here, 2.5. So with less than 4 inches of insulation, so 100 mil of insulation, 21 amps. More than 100 mil of insulation, you've got 17 amps. And if it's in the actual insulation itself or clipped down the center of the stud, well, now we can only get 13.5 amps. So that is a huge difference. So if you're putting that circuit on a 16 amp protective device, then you've got problems, okay? Now obviously the way you want to look at it is your worst case scenario. So if you come into an installation and most of it, okay, is clip direct, and there's only sort of 6 inches up to each socket, for instance, that's conduit in a wall, then you would go with the clip direct value. If you got up to, if more of the installation, so it's 50-50, okay, let's say 50% of the installation was buried in a wall or in thermal insulation, you would go with that value, okay? And the reason you're doing that is because you're protecting yourself, you're protecting the cable, okay? So you would then derate the circuit accordingly, okay, so it doesn't catch fire. So that's what I want you guys to think about when you're going out there. You need to go for the worst case scenario and use your engineering judgment to work out how to protect that cable by using the protective device. Okay. Once you've done your reference method, so that could be reference method B if it was in conduit or trunking on a wall, reference method F if it was on perforated tray, etc. You'd put that here, and then conductor detail. So your line conductor, the CSA of that. So for the lighting circuit, it might be 1.5. For the socket circuit, it might be 2.5 for the line conductor. The CPC then would be maybe 1 mil if it was a 3-core and earth. CPC for the socket circuit, that might be in dado trunking, and then because you're running it in singles, the CPC is going to be the same size as the line conductor, so that would be 2.5 as well, and then you would write that in there. You'll notice here I've put in a spare socket, and in each of those boxes I've put not applicable. Okay, you don't leave any boxes blank. Some people put lines through it. Personally, I think it looks more professional if you put not applicable, because then you can see that all the way through. If you've got a 3-phase circuit, you need to fill up all 3 of those lines. Some people put like a little, I don't know if you guys can see this, something like this to signify that all 3 are together. I don't know what they will let you do in the AM2, so if it were me, just to be safe, I would write 3-phase DOL in the centre of that, and then DOL either side of that, just to show that all of that's together. And then as I would be going through, I would still fill that out. So type, it might be a B type, but what I want you to do is do that all the way down, okay? The rating, let's say it might be a 16 amp. The braking capacity, well again, when you're looking at this braking capacity, guys, because you've got to select the MCBs before you put them in the board, they don't come pre-installed. Check that you can see that square box with the 6,000 or 10,000 written on the front. If you can't, it's probably on the side of the MCB or the RTBO, and before you install it, write it down and just make a note of it so that you don't have to try and remember or make a mistake or guess. Okay, chances are it's written on the front, but just be careful. So let's make the KA 10 KA. Most 3-phase stuff starts at 10 KA. RCD, well that won't be RCD. That won't need an RCD, so we will just put not applicable. And again, you see I'm filling it all the way down. Maximum ZS, so if I was to go to table 41.3, B type, 16 amp, 2.73. And again, I'll just put that all the way down, 2.73. Reference method. What could that be? And that could be singles in trunking, bit of SY flex down that might be on tray. I'd go for the worst case scenario, so that would be reference method B. Because being in the tray, being in free air, that can dissipate the heat easily. Being in the trunking with other cables, it won't. So I'll go for the worst case scenario. Line conductor for that, it's probably going to be a piece of 2.5, I'll take a guess. Again, you guys will follow the spec. So 2.5, 2.5, and if it's running singles, chances are that will be 2.5 as well. Let's down this one. So now that we've filled this out down here, we need to start doing some testing. To save yourself from getting confused, what you could do is anything that's not a ring, you can put not applicable in the ring continuity. Pen. So this is a 3-phase circuit over here that's not a ring. So I'm just going to put not applicable all the way through there. And then when I come to do the R1, R2 for this circuit, then I'm going to record each value. So for the line 1, I'm going to record the R1, R2 value in there. For the line 2, I'm going to record the R1, R2 value in there. And for the line 3, I'm going to record the R1, R2 value in there. And in that way, I can pick the highest one, and I know that that's going to be, my highest value for that ZS. Okay, so when I come over to here and I add up the ZS, I can then check that against the 80% value from the on-site guide or guidance notes 3, and confirm that that device is going to operate in a full condition. We now have to start doing some testing. Okay, we've got all the information off the board, of all the components. We filled it all out, we put all our data in. Now we're going to start doing some testing. So if you turn to page 41 in your guidance notes 3, you will see the sequence of tests. Okay, and the book follows the sequence of tests. So once you get onto this stage, have this book open in front of you, and then just turn the page, and the first thing it tells you to do is R1, R2 testing. Okay. The first thing you're going to do is you're going to check that you've got an earthing conductor coming from the isolator up to the board. You're going to check the continuity of that. You're going to check that it's complete. If you can visually see it and the connections are tight, then it's there, verify. The next thing you're going to check is that your bonding conductors are verified. Again, if you've installed them, you could just look at them and tick the box. Personally, I would be belt and braces. I would do a continuity test to the clamp. Okay, so disconnect it at one end so you get a clean reading. You don't want to pick up any parallel ways. And so you get your crocodile clip at one end at the board, and just test onto the actual clamp itself. If you test onto the screw that's holding the cable in, you should get a reading. If you then test to the pipe afterwards, the reading should be 0.05 higher, maximum. Okay, that's the reading they've kind of let you have. If you look at page 45, expected test results. Okay, so it says here, for joints across bonds by earth clamps and similar, the reading should approach 0.05 ohms, taking into account both the resolution of the instrument, its accuracy at low values, and contact resistance. Okay, so you should have only a 0.05 difference from the terminal that you've connected your bonding conductor into and the pipe itself. If you've got a higher value, your clamp might not be tight enough, your screw might not be tight enough, so just make sure. Okay, so then you've verified it. Once you've done your earthing conductor and you've done your bonding conductors, well, now we can move on to R1, R2 testing of radial circuits. So that would be your lighting circuit, or your boiler circuit, or your fire alarm circuit, motor circuit, anything like that, because they're radials. For this, you would put in a temporary link. So you're back to page 43. Okay, and for each circuit, they're suggesting you put a temporary link in, and then you check R1, R2 at each point through the circuit. Now, personally, I don't put that link in unless I have to. I usually like to actually take the line conductor out of the MCB and put it into the earth bar to get a good reading. You guys can do whatever you like. It all depends how well neatly dressed in the board is. Again, if it's all neatly dressed in and you've got zip ties holding it all in, which people may or may not like, you don't want to be pulling it apart to test it. So you can put a temporary link in. Obviously, because we're linking out line and earth, this board needs to be isolated before you've even started this testing sequence. Okay, this switch needs to be isolated and locked off, and proved dead, or there might be an isolator further back that should be locked off, and then you prove dead. Okay, especially if you're disconnecting earthing conductors or bonding conductors out the board. So just think about that. Once you've done your R1, R2 testing, of your circuits. And don't forget as well, for instance, if you've got two-way switching or intermediate switching, you need to make sure that you get the highest reading through all your strappers. So you need to turn the first switch on, the next switch off, the last switch on, recording these results as you go, and write them down as well. And then you go back again, so off, on, off, as you go back through, recording the highest. And you also need to do that with your insulation resistance when we get to it. With your motor, okay, that might be going through a DOL. You need to link out the DOL. So the readings, you don't take the readings at the DOL, you take the readings all the way at the motor. So you need to link them through. Now, whether you leave the cables, if they're singles, long enough to get to the other side of the terminals, or whether you have to put bridges in between, it's entirely up to you. Personally, I would leave the slack long enough to get to the SY flex. And then when I re-terminate it, I would put the slack back into the trunking. That's what I would do. Again, when you do the insulation resistance, make sure you leave those links in, because you've got to do insulation resistance all the way to the motor as well. Make sure that you've run a CPC to anything like the DOL. Just because you're getting an earth reading off the earth terminal, it may be getting a parallel path through the trunking or through something else. So just make sure that you've got CPCs at every point within the system, okay? Once you've done your R1, R2 testing, you then keep turning the page as we go. So we've done R1, R2 testing, we turn the page, talks about R2 testing. Now R2 testing is just the long lead method. So that's having a crocodile clip and a long lead on your earth bar, and then running round to each point in the system and testing that you've got an earth. If you do that, you've also then got to do the line conductor individually as well, which takes time. If you do your R1, R2 method, okay, and you're checking for switching in the line conductor only, so when you switch the switches off, you're checking your functional switching, you're checking that the circuit works. If you were testing at the light, for instance, every time you switch the switch on, you should get a reading. Every time you switch the switch off, then it should be open circuit, and on it goes. Same when you're testing your sockets. If you're testing your sockets, you should be checking in the line and conductor and the CPC. Every time you switch the switch off, it'll be open circuit. Every time you switch the switch on, closed circuit. And you should check both sockets if they're doubles on either side. Someone was saying that they got a socket from Screwfix a few weeks ago, and they terminated the CPCs into one terminal in the back of the socket, and when they came to do the testing, only that side had a CPC, an earth. The other side of the socket didn't, and you had to put a link in. So just be careful of that. You've got to check both sides of a socket. Because also as well in this, they're looking for the fact that the installation works, so it doesn't cost your company money to send somebody back if there's a faulty socket or something like that. So you have to be 100% positive that every part of this circuit works. So yeah, check both sockets. Once you've done R1, R2 testing, you've checked your functional switching as you go, you've recorded the highest results, then you move on to testing the rings. So bottom of page 45, it now moves on to continuity of ring final conductors. So all you're going to do is you're just going to follow this book as you go. Okay, so without this book, you're really going to struggle. First thing it says, we're going to check the end to end. Okay, so here, and this is where it moves to little r1, little rn, little r2 for rings. Okay, that's why it's little. You're going to do end to end of the line conductor, end to end of the neutral conductor, and end to end of the CPC. If they are all the same, okay, then the reading should be the same. So what I'm saying is, if the line conductor's 2.5 mil and the CPC is 2.5 mil, then the reading should all be the same. If they're not, then you may have a loose connection, and you should be aware of this and check through it. Okay, don't just write the reading down and assume it's correct. You've got to actually know that it should be the same, because the length of the conductor is the same, the size of the conductor is the same, so the resistance should be the same. If it was a piece of 1.5, which I don't think you're going to do in this instance, but if it was twin and earth, okay, so T and E, the CPC would be 1.67 times smaller, so the resistance would be that much higher, if that makes sense. So again, if I had a piece of 2.5 and I got a reading, and let's say that reading was 0.2, then my CPC for 1.5 would be 1.67 times higher. And I can check that by doing it on a calculator. If it's the same, then it's the same reading. Right, once you've done end to end, okay, so we're up here, once you've done end to end, you now move on to your figure of 8, and they want you to do R1 RN testing. So we're over here. Once you've done your end to ends, and I've just put in some theoretical readings here, because it's 2.5, let's say I'll get 0.2 on the line conductor, well, I'm going to get 0.2 on the neutral conductor as well, and then I'm also going to get 0.2 on the CPC. If it was 1.5 CPC, then it would be 1.67 times greater. But because you're running in singles, chances are these will be the same. But make sure you read the specification. You do whatever the specification does. Don't just think, oh yeah, I can run 1.5 as a CPC, if that's not what they've asked for. Once you've done that, you'll then do R1 RN. I've written up here R1 R2, but it's exactly the same. I could swap that out for RN. You want to do R1 RN testing. Here. That's what they've shown here, R1 RN testing. Now when you come to do this, what I want you to do, hopefully you can see this, let me just drop this down, titch. Okay. On the back of your test certificate, I want you to draw out the circuit, okay? I want you to write consumer unit, put a box. In here you're going to do the R1, R2 testing and you're going to record it. I want you to do R1, RN testing and I want you to record it. And then I want you to do the same at every socket that's on the ring, okay? R1, R2, R1, RN and record it. That way you're showing that when you work this calculation out, so let's talk about R1, R2 for a second because that's what I've got written up. Your R1 plus R2, you divide that by 4 and that will give you your R1, R2 reading. Then let's put some figures in there. We've got 0.2 plus 0.2, divide that by 4 and that would equal 0.01. Now because we've calculated that, okay, that's what we're looking for because we've measured the end to ends. Here are the end to ends. We've put the figures in, divided by 4, and that's what we've ended up with. What you now need to do is you need to test that at the consumer unit first. So when you put it in your connector blocks, you need to test at the consumer unit and validate this calculation. And you should be getting that at the consumer unit. If you're not, something's wrong, double check it. You may have had a loose connection somewhere or you may have added it up wrong. What you then need to do is go to each socket on that ring and you need to test it here, should get the same reading. Test it here, should get the same reading. Test it here, you should get the same reading. Now if you were to put in a spur, okay, so this is a 4th socket, let's say that's a spur. Well here my R1 and R2 and R1 and Rn are going to be higher because I'm no longer on the ring, because everything on the ring is always equal. I'm now spurred off the ring. I'm going to end up with a higher resistance here to account for this piece of cable, all right? And this higher reading is what I'm going to record into my R1, R2 for the ring. So for instance, let's say that I test this out and I get 0.01 here, I get 0.01 here because again it's the same size cable. I would get 0.01 there, 0.01 here, all the way around on the ring, should all be the same. Obviously you guys are going to test this, you're not just going to assume or write it in. When I come to do this, this might be slightly higher. 0.04 at the spur, That's what I'm going to put there. That would be my highest reading. Okay. When you do R1, R2, you've proved polarity. So I can put a tick in the polarity box. So here I can tick polarity. If you do only R2, you still need to prove polarity. So for instance, if I did that R2 long lead method on the CPC, so I clamp it onto the earth bar, I go around to each point and I dab it in on each earth terminal and I get a reading, I record the highest. That would go in here. I then need to put the clamp onto the line conductor and I need to then run back round to every socket or light switch and checking that it switches in the line conductor, and then make sure that I've got polarity, and only then can I tick this box. So R1, R2 testing, 2 for the price of 1. You get 2 tests for the price of 1. Saves a lot of time. R2 testing, you'll probably only really do that for checking bonding conductors, or checking that metal work is earthed. Okay. Right. Once you've done R1, Rn, you obviously then test R1, R2. So you're just going to follow this all the way through. In your figure of 8, I have done a separate video on R1, R2 testing. So if you want to watch that, it's on my YouTube channel. And that will talk you through what happens if you connect it correctly and the readings that you should be getting and why you're getting them. And also what happens if you not connect it correctly and why you're getting the readings that are different as well. It kind of explains that. It's about half hour long, so just be aware. When you're running the ring, if you're running it in singles and you don't want to lose track of that leg of the ring so that you can cross connect it and not get confused, I tend to mark one leg of the ring with a permanent marker, just a black dot or a black line, just to show that that is one leg of the ring. Some people use zip ties or electrical tape to tie the 3 conductors together for one leg of the ring. So the line, the neutral and the CPC, they use electrical tape to tape it together so that when they come to do the R1, R2 testing, they know which leg of the rings to cross over. So just be aware of that as well when you do it. Make sure you identify one leg of the ring so that you know how to cross it over. Once you've done your R1, R2 testing, okay, again it talks you through all this in the guidance notes 3. You're then going to move on to insulation resistance. Okay, so again, all I'm doing is following this book. If you've got this book and you're used to using it, this is going to be an absolute breeze for you. So insulation resistance, it says here on page 50 what setting that we're going to set that out. Because our line voltage is 230 volts, we're going to test at double the pressure. So we're going to test at 500 volts. And the reason that we do that is because we're putting the system under excess stress to see if there's any weaknesses. Same as in the same way that plumbers test their pipe work. So for instance, if the system was rated at 4 bar, they would test it at 8 bar maybe, to check that all the soldering's complete, that no speed fittings are going to pop off here or there. Because if it takes 8 bar, it will definitely take 4 bar, and it's exactly the same principle of what we do. If the system would take 500 volts, easily it will take 230 volts. Okay, it then tells you here that you can test the whole installation globally. You can do a global test. Now, doing a global test is quicker, but there are a few things that you need to be aware of when you do a global test. So for instance, if your RCBO is still connected, you need to disconnect that because that will give you a funny reading. Up here we have to make a list of anything that could be damaged while testing. So if you've got smoke alarms, you need to put smoke alarms on the smoke alarm circuit. If you've got any dimmers, you need to put that in, boiler, the direct online starter as well, any RCDs or RCBOs, any neons in the circuit, any lamps need to be disconnected or taken out. Any control gear, so things like the boiler, the boiler wiring, that all needs to be disconnected. and SPDs if the voltage is too high. So for instance, if you've got an SPD that's a 250 volt SPD, if you try and put any more voltage into the system over 250, the SPD is going to work and it's going to stop that voltage and it's going to deteriorate the SPD. So if you've got an SPD, the maximum voltage you can put in with it connected is whatever the SPD is rated at. So just be aware of that. And I know there's no SPDs on this, but just be aware of that in the real world, okay? Now, when you do insulation resistance, all of your bonding and your earthing all needs to be in place. Because you're putting voltage through the system, we don't want anyone getting any electric shocks. We don't want any stray electricity going anywhere. And if you've made a mistake, we don't want any metalwork becoming live. One thing I just want to point out as well, I have written it here. Dead testing is fault finding, okay? So when you're filling out this schedule of inspections, the R1, R2 testing, you're checking for continuity, okay? When you're doing insulation resistance, you're checking for cross connections in parallel, so short circuits, cross connections, that kind of thing, okay? So in a way, when you come to do the fault finding task and you're stuck on a ring and you can't work out what's going wrong, for instance, well, you could revert back to your dead testing of a ring to prove polarity, to prove your R1, R2, to prove your R1, Rn, and then insulation resistance to prove that you've got no short circuit. If you get really stuck, obviously that will eat up a lot of time out of fault finding. I am going to do another video on fault finding just to help you out. But I guess the reason I'm mentioning it, because a lot of people get confused when they have to fault find a ring. If you then just remember back to your EIC and doing the R1, R2 testing, if you've got a loss of continuity, then you do end-to-end, then you do R1, R2 or R1, Rn, depending on where the fault is. If you've got a short circuit, okay, you could do insulation resistance between each leg of the ring. Make sense? And effectively, that's what we're doing when we're doing these EICs. Before we put any voltage into the circuit, okay, any actual voltage, connecting the mains up and powering it up, from this point back, insulation resistance, continuity, that is proving the circuit is capable of taking electricity, all right? So I just want you to remember that. This point onwards, this is live testing. So the dead testing is fault find. So the test voltage here, we're going to be testing at 500 volts. So that's on page 50 in your guidance notes 3. So I would then put in here, I'm testing at 500 volts. And because I haven't done R2 there, that would be not applicable. I would then test live to earth. When I used to like the NIC, EIC model forms. I quite like those, and they would have line to neutral, line to earth, neutral earth. So you get all three tests. And I quite like that actually, because sometimes when you're doing testing on an EICR, for instance, it might be only one line, one conductor that's causing the problem, and it makes it easier to see that. The model form is obviously a very basic form, and it doesn't even show R1, Rn testing. And I mean, what's the point in doing the testing if you're not going to record the results? So, if the IAT are watching this and they're listening, I think it might be a good idea to, make a column for R1, Rn testing, and that way apprentices won't get confused, because then no one's doing it in the real world. I promise you this now, guys. I don't know anyone that does R1, Rn testing of a ring. Everyone just sees R1, R2 on here, and that's all they do. If we had the column, people would then do the test. I can't see why you wouldn't have it. Anyway. So when it comes to doing live to live, what they're talking about there is your line conductor to your neutral conductor. They're also talking about your line conductor L1 to your line conductor L2 to your line conductor L3, all of those three to neutral as well, okay? So don't forget to do all of those. Again, if you're doing it globally, over the whole board, all you'll do is you'll put your clamp onto the neutral bar, and then you'll do L1 globally, L2 globally, L3 globally. And then you'll do L1 to L2, L1 to L3, L2 to L3. And if you guys think about this as well, because I will talk about insulation resistance here. Insulation resistance is exactly the same amount of tests as your safe isolation. There's 10 tests. So I've got earth to neutral, 1 test. I've got earth to L1, that's 2 tests. Earth to L2, 3 tests. Earth to L3, 4 tests. Then I've got neutral to L1, 5 tests. Neutral to L2, 6 tests. Neutral to L3, 7 tests. Then I've got L1, L2, 8 tests. L3 to L1, 9 tests. And L2 to L3, 10 tests. Okay, 10 tests on the 3-phase circuits. Also as well, which I'll come back to later on, when you're doing resistance in parallel, okay, remember back to your science and principles section, you're doing the reciprocal of the resistors. So for instance, you would, to find the 1 over RT, it would be resistance 1 over R1 over 1 R2 over 1 R3. So all of these resistances down here, you would do that to the reciprocal of that to find out the whole resistance of the installation. So a lot of people think that, you know, 1 megohm is the minimum for each circuit. It's not for each circuit, it is for the whole installation. And again, I don't know why this isn't on the form, or why we don't, you know, it's not even in guidance notes 3, it doesn't talk about it. But you need to do the resistance of the whole installation, and if that was below 1 megohm, then you've got problems. And I'll talk through that in another video, but just be aware of it for now. So don't forget resistors in parallel for insulation resistance. Okay, we'll come back to that in a second. So once we've done our lives to lives and our lives to earth, okay, all 10 tests for a 3-phase, we would write the results in here. At this point, we've done all our dead testing. So make sure you do all your circuits up to this point. So each circuit, one at a time, do your R1, R2 testing for radials, do your end to ends of your ring, then you do your figure of 8 R1, R2s, figure of 8 R1, RNs. You're at this point here. Then you're going to do your insulation resistance of the whole board if you can. So then you're here, you've done all of that. You then prove polarity because you've done R1, R2 testing, so you've proved your polarity. At this point, this should all be filled out and level. Then you move on to the live testing. And before you go on to live testing, you have to prove your polarity coming in. So if we turn over the... Okay. So once you've done your dead testing, you move on to the live testing. That's when we're going to prove automatic disconnection of the supply. And this is where you need to work out your R1, your ZS. Okay. So your maximum measured, your ZE or your ZdB. Add it to your R1, R2, which would be here, and that will give you your measured ZS. Okay, your measured ZS. Now your measured ZS needs to be lower than the 80% value, not the maximum value in BS7671. So this table here, 41.3, okay, that is your maximum ZS, okay? That's not what you're comparing it to. What you're comparing it to, sorry, is 80% of this value. So for instance, if I took a 32 amp B-type MCB or RCBO, that would be 1.37, my maximum ZS, 1.37 ohms. I then times that by 0.8 and that will tell me my 80% value, which would in fact be 1.1 ohms. This figure here, if it was for a ring, would need to be less than 1.1 ohms, not the 1.37 ohms. And the reason for that is the 1.1 ohms, that's your hot value. Okay, the circuit's warm, it's in use. Also as well, that at different times of the day, the voltage outside can go up or down slightly. Resistances in the ground can go up or down slightly. So we need a little bit of tolerance. We don't work at the maximum values, okay? Reason being is that if I spin this round, okay, so let's discuss why R1, R2 is important and R1, Rn obviously, even though we don't record it. The reason that we record R1, R2 is because with twin and earth, the CPC is usually smaller. So by doing the adiabatic equation, you can prove that it can handle the fault current and that the MCB is going to trip out. So if we record the highest value, then the R1, Rn, which should then be lower, will definitely comply. And I think that's their thinking, even though personally I would prefer that we had R1, Rn recorded, okay? But that's a different story. So why is it important? Well, up here I've just written out ZE for a TNCS, okay, so 0.35, that's what it should be maximum. I've then put R1, R2 testing, and I've put what the maximum ZS is for a C32 MCB RCBO, okay? So let's look at the two situations then. So 0.35 ohms ZE TNCS. If we were looking at 0.68 ohms, which is from table 41.3, okay, so C32 0.68 ohms, okay, from table 41.3, that's our maximum ZS. Well, that only gives us 0.33 ohms maximum R1, R2, okay? And the reason that is also a problem is because the amount of current required to operate a C32, okay, MCB or RCBO, in under 5 seconds is 320 amps of current, okay? Now, the conductor will take that, but for a very short period of time before the insulation heats up and deteriorates and the cable melts and catches fire, okay? So it will handle that amount of current, but only for less than 5 seconds. If you turn to, and I've put it here, page 371 in BS 7671, that will take you to the 371, that will take you to BC. That will take you to these time charts, okay? And this is basically the trip curve of a C-type MCB, an RCBO. And then over here, they've already worked out that to trip out in under 5 seconds, 32 amp needs 320 amps of current. Now that's 10 times the current rating. So if it's 32 amp, 10 times 32, 320. For a B type, it's 5 times. So 32 amp times 5, 160 amps. For a D type, it's times 20, so it would be 640 amps. And that's how they work it out. Then if you look at this trip curve, okay, so we've got time in seconds across the top, and we've got current across the bottom. So prospective fault current in amperes across the bottom. And then effectively what happens is you work your way across in current. So if we were looking at 32 amps, we would be down here somewhere. So in between 10 and 100. So 10, 20, 30 would be over here somewhere. In fact, it would be more over here somewhere. You can see where it is over there. So if for an MCB to trip out at 32 amps, it actually needs 10,000 seconds, okay? So that's about 3.5 hours of that cable heating up. And it will take it, but it takes 3.5 hours for that MCB to trip out. If you want that to then trip out in under 5 seconds, obviously we need the 320 amps of current to help that happen. And if you look at this curve here, so there's 32 amp, the more current that you put in, the quicker the trip time gets. Okay, so the more current obviously swings round to the left, but the quicker the trip time gets. As simple as that. So that we need that to happen quickly so the cables don't deteriorate. So a lot of people think that a 32 amp breaker will trip out at 32 amps. Well, yes it will, but only after 3.5 hours. So if you've got a really high resistance in the circuit, that current cannot flow. I've also made a note here, the UK voltage. Okay, so the UK voltage is being harmonised at 230 volts, and that's plus 10% or minus 6%. Okay, so that gives us a voltage range of 216.2 volts to 253 volts. Now that's important because obviously to get this 320 amps of current, we need to go back to Ohm's law. Most thing in the electrical world goes back to Ohm's law. So the voltage, if we do it at the lowest voltage, because that will give us the worst reading, 216.2 volts divided by, so we'll do the 0.6, we'll do the maximum value first. So divided by 0.68 ohms, well, that only gives us a current of 317.9 amps. So that MCB is going to take longer to trip out, okay? And that is without even taking into consideration the heat of the cables, okay? So obviously these are that maximum ZS is the cold range, okay? The 80% is obviously the hot range, hot readings. So that's not taking into account greater resistances due to the cable being warmer or any other influences inside the building, okay? So even before we've even got started, we're already disadvantaged, okay? So the reason that we have an 80% value is that gives us a tolerance, okay? So here, if we do the same calculation again, but with the 80% value, so we've got 216.2 volts, divide by 0.54 ohms, which is the 80% value, okay? Well, that gives us 400 amps to play with. So the reason that makes a difference is because we've now got 14 ohms of resistance that can go up or down in the house, which is going to change this amount of current that will flow. Okay, so we've got a bit of a tolerance. That's why you should never work to the 100% values, okay? And the assessors are going to want to know that you understand that. So what I want you guys to do, and I've got it just written here, is in the remarks, okay, I want you to write in your maximum ZS from column 8, which, and if you look at the, if you look at all these columns, they're all numbered. So circuit number, that column is 1. I don't know if you guys can see that. So that column is 1, then 2, then 3, then 4, then 5. So if you look at column 8, that is your maximum permitted ZS. That's from the book, so table 41.3. So I want you to take that maximum ZS, times it by 0.8, so that will give you the 80% value, or you could just look in the on-site guide or guidance notes 3, and that will be on, in the on-site guide it will be appendix B, which is on page 131, or it will be on page 142 in guidance notes 3. Okay, depending on which book you're using. But if you've calculated it, your measured, okay, so if we come over here, your measured value, okay, which is your ZE plus R1 plus R2, needs to be lower than the 80% value that you're going to work out over here. And I want you to show the workings out, because then that will prove that you understand what you're talking about. Now, because you're not testing at the origin, okay, of the installation, you'll probably find that your ZdB is going to be extremely high and it won't pass. Do not be afraid to fail this, okay? Because they want you to understand that this doesn't pass. Just because it's a new installation, it hasn't passed, at which point, you know, the supply needs to be upgraded to that dB. But they want you to be able to fail it, okay? So if it doesn't pass, right in there, fail. All right? Good. Okay, so hopefully that now makes a bit more sense to you. That's why we go with the 80% values. 320 amps of current to trip a C-type 32. Okay, the voltage could be as little as 216 volts in the UK. And then if we divide the volts by that resistance, we only get 317.9 amps of current, which isn't going to be enough to trip that breaker out in under 5 seconds. So then it doesn't comply. Okay. Now when we come back to guidance notes 3, and we're back into proving protection. So we're on page 65 for protection by automatic disconnection of the supply. That's where this, you're proving it. You're proving that the supply is going to disconnect in those times. Okay. Without doing that calculation or proving it, you can't prove that. Does that make sense? Okay. Obviously, in the real world, we can use RCDs to get around that, but that's not in the AM2. We can talk about that way down the line. Okay. So we've done our fault loop impedance. I'm then going to turn the page to page 66, and I've highlighted some key points here. So the first one is, so there are 2 methods for verifying total earth fault loop impedance for a circuit, and so measurement of R1 plus R2 and adding that to the external earth fault loop impedance, ZE, okay, and that will then give you your ZS. Does that help? Oh, I haven't really got it in the right place. Does that help? So it says everything that I've just said, it says on page 66, and it describes it for you. It's even got the calculation at the bottom. So ZS equals ZdB plus R1 plus R2, and that will give you your ZS. You're then going to take a measurement of your ZE. Okay, so now we're on page 67. Let me just put this back to where it was. So thanks for sticking with this, because this is obviously an absolute marathon to get through this, and there's so many things to consider, and I've probably maybe said a few things wrong. I'm going to go back through this video and check it over. But basically at this point we have done all our dead testing. We've done our R1, R2 testing, insulation resistance testing. We've confirmed polarity, okay, with the R1, R2 testing. We've taken our maximum measured ZS, which is our ZE plus R1, R2. I've just taken you through why that's important and why we work to the 80% value. Okay, and now we're going to be moving on to proving the ZE. Okay, so with your main switch open, so basically with it off, you do your ZE. Okay, now you do ZE with the main earth disconnected. Okay, and the reason that you do that is because you want a clean reading. What you're measuring is the resistance from the transformer all the way through underground to the supply head, or wherever it is you're working, could be the DB. But if you're doing ZE, it's at the supply, so it'll be at the head. And then you're measuring the earth fault path back to the transformer, okay, in a loop. If you've still got your bonding connected in place or parallel paths and we're picking up another earth, obviously that reading is going to be artificially low. It's going to be a lot lower than what it is. You know, especially because, you know, if you've got metal pipes coming out of the ground, so let's say gas pipe, water pipe, both coming out of the ground, effectively you've got 2 earthing rods, okay? So we need to make sure that we've got those disconnected and we're purely testing the supply. And the reason that you then have the main switch off, for obvious reasons, is because you've disconnected the earthing system to the whole installation. Okay, so that needs to be secured and locked off in order to complete this test. Now the test that they're showing you here is a 2-wire test. So you have 1 probe on the line conductor and 1 probe on the earthing conductor, and it's a crocodile clamp. You wouldn't be holding that with your finger, okay? It'll be a crocodile clamp. Once you've done that, obviously that's for a single phase, I should point out as well. So that's for single phase. If you're doing 3 phase, you've got to do L1 to earth, L2 to earth, L3 to earth. So I've kind of drawn that up a bit here, okay? If I close that, that might help make it a bit more logical. So I don't get so confused with everything going on that side. So your ZE or your ZdB, because you guys aren't connected to the to the supply, you're going to do between earth and live. So earth to L1, earth to L2, earth to L3. So that is your earth fault loop impedance, right? Once you've done that, and I want you to record all three of the figures, okay, not on the actual certificate itself, on the front in the schedule, but I want you to do it on the back to show the instructor, the assessor, sorry, that you've recorded the highest. Okay, so all of this that I've got written here, I want you to have all this written on the back pretty much, or on a piece of paper somewhere, just evidence that you know what you're doing. So earth to L1, earth to L2, earth to L3, record the highest reading, okay? And that is the figure that will then go into the box, okay? And I want you to record that, and I want you to record that up here, okay? So ZS at dB, and that's where you're going to record that reading, okay? We're now going to do perspective fault current. Now, perspective fault current is the maximum amount of current that's going to flow in a fault condition, okay? So the closer that you are to the transformer, the higher the fault current, because again, it all comes back to Ohm's law. The more resistance in the ground, the lower the current at the other end. If you imagine it's a bit like a hose pipe at the tap, it's absolutely gushing out, okay? Loads of pressure. You put on a metre of pipe, it slows it down. You put on 25 metres of pipe, by the time you get to the end of that hose pipe, it's literally just dribbling out the end because of the resistance in the circuit. It's the same sort of theory, same principle. So, closer you are to the transformer, the Ka is going to be very high. The further you step away from that transformer, more resistance is added in until, you know, and the current goes down as a result. So when you do the perspective fault current, okay, this is now 6 tests. Okay, so perspective fault current, which we're measuring in Ka, we're going to do L1 to earth, L2 to earth, L3 to earth. We're then going to do neutral to L1, neutral to L2, neutral to L3, and we're going to record all 6 of those values. I want you to then take the highest value and I want you to double it, because it's a 3-phase system. As a rule of thumb, if we double the highest reading, then we're covered. Okay, that's the worst case scenario. And it tells you all this on page 68, 69. It says here, page 69. So with some instruments, the voltage between the line conductors cannot be measured directly. Where this is the case, it can be assumed that for 3-phase supplies, the maximum balanced prospective short circuit level will be, as a rule of thumb, approximately twice the single phase value. This figure errs on the side of safety. Okay, so whatever the maximum is, and show the assessor that you've worked out which one is the maximum by writing them down. Okay, it doesn't take much. Take the maximum figure and double it. And again, that is what you record back on this schedule of results, schedule of test results up here. So Ka rating at the dB. Okay. Now, why is that important? Well, basically, in a nutshell, the Ka value is the maximum fault current. The PFC is the maximum fault current that's going to flow in a fault condition. Okay. Now, whether that's line to earth or line to neutral, you have to record the highest, and if it's 3-phase, you have to double it. Okay. And you do L1 to earth, L2 to earth, L3 to earth, exactly like I've got written here. Neutral to L1, neutral to L2, neutral to L3. And then double it because it's 3-phase. Now what that means is that when we choose our protective devices, our MCBs and our RCBOs, they need to have a Ka rating higher than the perspective fault current coming into the supply, coming into the building. So it's no good having a Ka of 8 Ka coming in, perspective fault current of 8 Ka, but we're only selecting 6 Ka devices. Because in the worst case scenarios, it might blow open, at which point it's completely unreusable and you have to change it and fit new. Or another worst case scenario is that it actually fuses together, okay? And then you've got no protection whatsoever and current's just flowing and flowing and flowing until everything catches fire and melts, and then it gets disconnected. So that's why we need to have the KA rating of the devices higher than the KA, the actual respective fault current coming into the building. Does that make sense? Obviously, as you go through the circuit, so your highest reading is always going to be at the supply. As you add more resistance into the circuit, again, simple Ohm's law, current cannot flow as far. Okay, think about the hose pipe again. So again, at the supply, we've got quite a bit of pressure. As it goes through the resistance in the circuit, by the time we get to the end, it's dribbling out the end, which is why we always need to run bigger cables to get more current available at the other side, at the other end of the installation. Okay, the rated short circuit capacities of devices is on page 71 of GN3. Okay, so that's here, and it tells you, so let's have a look, BS88-2, 80 kA at 400 volt, 50 kA at 230 volt. Domestic fuses, okay, so type 1, type 2, so 16 kA or 31.5 kA. Circuit breakers to 60898, so we can get them at 1.5 kA, 3 kA, 6 kA, 10 kA, 15 kA, 20 kA, 25 kA. Obviously, you have to be you find maybe 25 kA, you might be in a shopping centre and they've got their own transformer and you're right next to it. And then you've got 1361 fuses, okay. So type 1, 16.5 kA, type 2, 33 kA. They've now been withdrawn and replaced by the 88-3 system C. And then circuit breakers to 3871, they've now been, they don't make those anymore. But if you do come across them, they have M1, M1.5, M3, M4.5, etc. And that is the same as their KA value. Then you do your phase testing. Okay, so for the phase testing, what you'll end up doing is you'll end up, if you've got a 2-probe tester, let me see. So you've got a 2-probe tester like this one, for instance. This is from TIS Solutions, or Test Instrument Solutions, so I say. What you would do is, these are handed, so you've got L1 and you've got L2. And to test the phase rotation with this, you would put probe L1 onto L1, probe L2 onto L2, and it should be rotating clockwise. You then put L2 to L3, okay, so you've literally just moved from there up, and you do L2 to L3, and again, it should be rotating clockwise. You then put probe L1 onto L3, and then L1, and then it should be rotating clockwise. So literally, you've just gone L1, L2, L2, L3, L3, L1. Simple as that. In fact, I'll show it here. I'll do it this way around because this is the way probes are. You do L1 to L2, rotating clockwise, L2 to L3, rotating clockwise, and then L3 to L1, rotating clockwise. Simple. They might give you a 3-probe tester. And again, it does talk about this in the book, and they usually have some sort of dial or something along those lines. And in that instance, there's 3 probes labelled L1, L2 and L3. And all you do is you put probe L1 on L1, probe L2 on L2 and probe L3 on L3. And then it should be rotating clockwise. And you may have to press a button. It may be a spinning disc or it may be an LCD display. That's it. Then you've proved polarity coming into the building. If you've then done R1, R2 readings all the way throughout your installation, then you've also confirmed polarity through the building. It's as simple as that. We then move on to, so let's finish with this. We then move on to testing the RCD. Okay, for fault protection, which this in your AM2 it won't be, it needs to be 300 milliseconds. And for additional protection, so if you've got sockets or bathroom lighting or an outside socket, okay, it needs to be for the 5 times, okay, so for additional protection, so it needs to be 40 milliseconds. So whatever you read here needs to be less than 40 milliseconds. Now, obviously, when you still do your RCD testing, Okay, and those figures are on page 75 as well. There's a box here that tells you all about it, and it talks about additional protection underneath. What you then need to do is you do your normal testing. So you need to do your half times test to make sure that the RCD isn't too sensitive. You'll then do your 1 times at 0 degrees, 1 times at 180. You'll then do your 5 times at 0 degrees and your 5 times at 180. And then you'll record the highest of the one that you need. So if it's for fault protection, it'll be the highest of the 1 times at 0 or 180. Or if it's for additional protection, where you've got a 30 milliamp RCD, and it'd be 5 times, so it'd be the highest of the 5 times at 0 degrees or 180 degrees. And that's the figure that you record in here, okay? You then need to remember to test the button. And that's just pressing the button on the front. Functional testing, does it work? Tick. On these certificates now, obviously we've got AFDDs. There's not really much you can do with an AFDD. There aren't any AFDDs in the AM2 currently. So in here, all you would put is a not applicable. Okay, job done. And that is it. You've worked your way all the way through to page 80. Job done. Okay. So up here, we've got details of test instruments used. Basically, because this is a legal document, your testers need to be calibrated, and it ties that tester to this document. So that if there was a fault, let's say there was a fire, they might ask you to pull up all the certificates for that tester. Okay. It also helps you as a tester, as when you go around doing testing, if you start to notice that your meter's out of calibration, what you're then supposed to do is go back over your certificates that have been tested by that tester, and you're supposed to sample them to make sure that your tester is accurate again. And if they're not, you've got to retest it. Okay, so here you will just put the serial number that's on the MFT, and it won't be the model number. All right, it won't be the MFT 1553 or 17 series. It will be the registration number, the serial number that's on the bottom, and it will be a long number. It will be something like 000/000/something. Okay, that's what you need to record up there, or an asset number, but chances are it'll just be the serial number for your AM2. You also need to make sure it's calibrated and in date. And that, I think, is pretty much it, guys. So, you know, I appreciate you watching the whole of this video. It was pretty long. Okay, if you've made it this far, then thank you. I promise you it's even longer when you're recording it. If there's anything else that I can do to help, then let me know. And if I've missed anything, let me know. But effectively, you need this, guys. Without this, you're going to really struggle, and just follow it page for page. Okay, I hope this video has been good. Any questions, let me know.